Okay, so, to avoid confusion between current, voltage, and resistance, just think of a situation where you've got a given voltage and you can vary the resistance. The current you get is going to be bigger if you got a bigger voltage, right?
Right.
It's going to be smaller if you got a bigger resistance.
Right.
These are proportionalities, so the current, now, you have to observe things and then work out the theory to understand as best we can why this is the case, right? But simple observation that you've done in lab supports this, and you want to think through just what you did in lab that would make this plausible and how you would further test it to make sure that the proportionalities are precisely what we think they are, okay? But we say that the current is proportional to voltage and inversely proportional to resistance, so it's proportional voltage over resistance, okay? And then declare the proportionality constant to be 1, okay? Give it the name ohm. And that would be the proportional constant in SI units, okay? Simply meaning, well, in SI units, this is the amp, and this is a volt, right? So if this is in amps, this is in volts, and this is in ohms, then you can simply write, well, I keep wanting to write it another way because I memorized this in high school without thinking through the proportionality. But to my high school's credit, they did teach me proportionality before I graduated. Okay? So I knew how to do proportionality and think in terms of proportionality. I just didn't bother to do it here because the two didn't coincide and I wasn't smart enough to put them together. Okay? Now I used other heuristics to make sure I had this correct. The way I remembered it was E equals IR. Used E instead of V for voltage, and that's legitimate. Voltage is an EMF, okay? EMF is kind of a more general term. So, I've got that firmly entrenched in my feeble mind, okay, and I'll never get rid of it. But I don't use it. Even now, I think in terms of common sense and proportionality. Just take a situation where I either have a known current and resistance, want to find the voltage, or and want to understand the proportionalities, or more directly, if I know what the voltage is, I put a battery across a piece of nichrome wire, right? Because that's what you did. Longer piece of nichrome gives you more resistance, gives you less current. So for a given voltage, okay, I get less current for the resistance, therefore the inverse proportionality. And if I increase the voltage, I very naturally as expected, do observe that I get more current, right? Okay? And anytime you want a piece of nichrome and a couple of batteries and something to detect current, like a piece of aluminum strip over a magnet, you can observe this. Now, if you want to get fancy and use a meter, then you get a more accurate measurement of current, right? But with just that simple apparatus that gets back to the very fundamentals, because you don't know what goes on inside that electronic meter, and you're not quite sure what goes on inside an analog meter, although that's easier to understand, okay? You can confirm that if the proportionalities are direct, are with the first powers, that this is the way it has to be. Okay? Now, you can't precisely measure the fact that these are first powers unless you have a good meter, okay? And a regulated source and all that sort of stuff. But it's very important to understand where this comes from so you can go back to direct experience and never have to ask, like, what does an ohm mean? And don't be embarrassed because you did, okay? It's the thing that goes with amps and volts in this relationship, okay? So one way of answering that is it's, well, R is V over I, right? So it's a volt per amp. That's what an ohm is, okay? And you can reduce that to fundamental units. Volt being a joule per coulomb, an amp, and so forth, okay? So you can reduce it down to amps and time, okay? And mass, okay?